Hello, my name is Bryant Miley, and this is my Physics 2211 Projectile Motion Lab. So to get started, we're going to cover the introduction, including the models that were relevant to this specific experiment, as well as talking about the actual experiment itself, the coding portion in GlowScript, as well as discussing the results and drawing some conclusions. So for the introduction and models, the purpose of the lab was to predict the future motion of an object given its initial conditions and the forces acting upon the object, which were, in this case, gravity and drag. So this involves Newton's second law to produce the position update formula to track the motion of an object. And it also involves drag or drag force. So here's a preview of the results. This just shows the visualizer as well as the visual and the graphs that were put out by tracker or not tracker the coding portion, and these specific graphs are for the no drag part, but we also calculated for the drag, including drag. So for the experiment, a wadded up paper ball was thrown up into the air, forming an arc motion, which then descended until it hit the table. Due to the blurriness of the video, it had to be guessed whether the center of mass was located for the ball in certain frames, and I had to start tracking its motion later after it already started descending, because when it was thrown up, it briefly went out of view in the top portion for a few frames, and this caused the y component of my initial velocity conditions to be negative. Here we used a yardstick as the calibration stick or the point of reference for the distance that the object traveled. So this is the coding, this is the initial conditions, including the mass of 0.0045 kilograms, and then we also have the initial position, which is just vector 0, 0, 0, and the initial velocity, which is vector 0.962 negative 4.8120. And then the delta t is just the size of each time interval. And so here's the code with drag up here, or without drag, sorry. You can see the b value equals 0, but with drag it equaled 0.0147. And everything else is the same. We have the calculation loop here where we have our calculation for fnet as well as the position update and velocity update formulas that help us track or calculate the motion of the object. And so to discuss this a bit, margins for error in this particular experiment would include air drag on the object and the table, as well as the fact that the ball was blurry in the video, which made it harder to accurately track its center of mass, and thus it makes the results less trustworthy. And so for conclusions, we have a couple of questions. Do any of your models predict a terminal velocity? Well, in this case, if an object had been thrown like straight up into the air with like the same starting speed, then it would take like a lot longer to eventually hit the ground, and this is all because all of the speed would primarily be focused in the y component of the velocity. And what for the second question, would the time this object takes to reach the ground be the same, longer, or shorter than the time it took in your original experiment. My current model doesn't help me predict terminal velocity, but you could, like in a similar experiment, you could throw the object from like a much higher place.